Good morning, and thank you for the invitation at this second edition of the Computational Data Neuroscience Symposium. My name is Alberto Feletti, and I am Associate Professor of Neurosurgery at the University of Verona in Italy. Today I will be talking about the development of a Meningioma database for deep learning projects, why we need one, and how I do it. I have nothing to disclose. Looking at what has been done in terms of deep learning work in neuro-oncology over the last years, we can see that there has been a great deal of interest in the study of glial tumors as well as metastatic tumors. As these are currently the great unsolved problems in neurosurgery, it came naturally the will to apply the great potential of deep learning to try to extract every additional piece of information that could help improving the prognosis and the care of the patients. The majority of applications is being developed with regards to neuro-oncological imaging, in particular MRI. And here we can see some of the outstanding work that has been done so far, where deep learning has been used to automatically segment tumors and edematous regions, to extract useful tumor features for analysis, to try to predict relevant prognostic histological information even before the patients come into the OR. And we start to see some very promising results. What about meningioma patients? Meningioma is the most frequent benign brain tumor and a disease which is not uncommonly encountered in the clinic as well as in the OR. Is there any potential to apply deep learning techniques to improve both clinical workflow as well as patients' outcome? To answer this question, we first have to take a look at what entails for the neurosurgeon and the patient to deal with a meningioma. We are talking about a tumor which is usually single, but can also present with multiple lesions. Depending on the dimensions, location, and clinical condition, there is the option to follow the patient over time and observe the growth of the tumor, or to decide to surgically remove it, or even to use radiation therapy. When a decision to bring the patient to the OR is made, a detailed surgical planning takes place involving tumor segmentation, both to calculate the volume and to be used for neuro navigation. The evaluation of tumor location and consistency based on the preoperative imaging helps to inform the patients on the chances to remove the tumor completely or not. Then, once the surgery is over, a follow-up strategy is implemented, which is particularly important for patients in whom a radical resection couldn't be achieved. If we look at the strategy involved in the care of patients with meningiomas, we can see that there are multiple areas where deep learning, with particular focus on imaging, could make a meaningful difference in the management. Particularly, the use of a supervised learning approach could be used to extract meaningful information for the preoperative MRI as tumor volume and to segment the lesion itself in an automatic and effortless way. If detailed enough, this mask could be directly sent to the navigation software and be used in the OR. The same type of information can be applied also to the conservative management of meningioma patients. In this case, we could easily and accurately follow the growth of the tumor over time, allowing a more precise definition of the follow-up strategy. We could also think to apply deep learning techniques with prediction purposes. One example could be to try to predict the consistency or the histological grade of the tumor. Both will help the surgeon to plan the operation, as well as improve the information given to the patient on what to expect in terms of surgery and prognosis. Looking at the literature, we can see the interest starts to rise, but is not at the level of malignant tumors, regardless the fact that meningiomas are the most frequent primary brain tumor, accounting for almost 34% of them. These works, while presenting good results, are mostly based on small data set of around 100-120 brain MRIs, and of tumors fairly similar to one another. In the realm of deep learning, it is not a great number, in particular if we make a comparison with those algorithms trained on hundreds of thousands, if not millions of images. This is one of the most important limitations in developing algorithms that are reliable and generalizable, regardless of location, dimensions, numbers of tumors involved. And meningiomas present a great variability in terms of these features. The Department of Neuroscience of the University of Verona joined a project of creation of a meningioma database started at the Brigham and Women's Hospital last year. The idea is to create a dataset including meningiomas of all types, locations, and dimensions in order to represent the meningioma patient population in the best possible way. The dataset, which is currently under continuous development, includes the images themselves, patient basic demographic information, information related to the image acquisition and the MRI machine itself. It also includes the segmentation of all the tumors, which is done on T1 plus contrast sequences. This database currently includes about 1,200 MRI scans with a series of variables which will allow the development not only of deep learning projects, but also traditional statistics and epidemiology. We can see here some summary statistics which resemble some key epidemiology data about meningioma that we find in the literature. For example, mean patient age and the gender ratio, which notably favors men. We were also able to extract the weight of patients from the DICOM files. With regards to tumor features, we can see that most patients present with a single tumor, but scans with multiple tumors are significantly represented as well. We see also that the most represented location is the cranial vault. We were able to obtain histological data for about 1/3 of the patients, with the majority represented by grade 1, followed by grade 2 and grade 3. When it comes to these types of projects, it becomes important as well to have information about the MRI machine and image acquisition modalities. We included in the database the strength of the magnetic field, which in the great majority of cases is 1.5 Tesla. The period in which the exam has been taken is important, because the machines evolve continuously, and in our case, we have scans that were taken back from 1996 up to 2018. A list of additional physics parameters is listed here, which could be of more interest in the study of the underlying structure of the images themselves. In order to develop a database like this, that could be maintained over time, that is reusable and that is up to standards, some considerations must be done. First of all, we are considering patient-sensitive data, and so to ensure the respect of privacy is of paramount importance. This includes two main actions when it comes to imaging data: the removal of the information stored in the DICOM files, which can be easily done through a file format conversion. In case of brain CTs and MRIs in particular, it is also regards defacing the scan itself using a defacing software. The nice thing about DICOM form is that it stores a lot of information about the patient, the machine, and the exam itself in the same place, and we were able to extract all the information included in the database from one file alone. The downside is that careful anonymization must take place. Secondly, we must be thoughtful of what to include in the database in order to avoid the need to go back and extract additional variables we hadn't thought about initially. And finally, there is the need to keep the database up to date in terms of maintaining the existing files, regulate storage and access, and to enlarge the database itself, considering how important this is to provide deep learning algorithms with new data and the importance of a high performance and reliability of such algorithms to be used in the clinical practice. In this spirit, we started a collaboration between our two institutions. The idea is to plan the deployment of the database in order to allow research groups around the world to train and test their algorithms on a common basis, and at the same time develop a network of collaborators who, on one hand, would contribute to the development and improvement of the dataset itself, and on the other could take advantage of big, carefully curated and up-to-standard resource for the advancement of research on meningiomas and care of affected patients. Thank you.